Hello, everybody. Hello, everybody. I'm going to give you a lecture on an action potential. So to start, what I've done is I've drawn a half of a neuron on the whiteboard here. Here we have our dendrites, here we have our cell body, and here we have our axon. This is all membrane, and as we're going to see, the membrane is where all the action takes place, no pun intended. So as you already know, when we talk about neurons, the dendrites and the cell bodies are programmed to receive. So all stimuli from other neurons or some other source are going to stimulate the dendrites and the cell body. And I'm going to focus on the cell body with my illustration. Now, if those stimuli coming from another source are strong enough, they will cause the action potential to, I'm sorry, the axon to have an action potential. So let's get started with the what's known as the resting membrane potential. What this means is that we're going to have charged ions on the outside of the cell and we're going to have charged ions on the inside. This actually creates voltage because separation of charges is what creates voltage. Now, this isn't like a battery where you have electrons flowing from a positive side to the negative side. Instead, we'll have our membrane, which we see right here, which is going to have positive ions on the outside and less positive ions on the inside. That's going to give us our differences in charge and therefore give us polarity. So when I talk about the ions, what I'm talking about is sodium and potassium. There are other ions involved, but those two are the big two, top two. So what I've done is I've drawn sodium. I'm going to use little circles to show sodiums in the cell. And for potassiums, I'm going to use little triangles. So when we have a resting membrane potential, this is achieved by an enzyme in the membrane called the sodium potassium pump. Sodium potassium pump is a protein that uses active transport to pump sodium to the outside of the cell and potassium to the inside of the cell. So I'm going to draw a little a circle, if you will, in the membrane, and this is supposed to be the sodium potassium pump. So let's say we have our sodium potassium pump here. It's often drawn to look something like that. But and ATP, which is three phosphates attached to a nucleotide. When ATP breaks off, it provides energy for this enzyme to move, pumping three sodiums to the outside of the cell and two potassiums to the inside of the cell. Now, there's more than just one sodium potassium pump. There's trillions of them found in your brain and so forth. And it turns out 20 to 40% of the energy you use in your brain is spent on these sodium potassium pumps that are constantly pumping sodium out of the cell, potassium in. Now, let's see why this is so important. So there goes our sodium potassium pump. We know that it pumps sodium to the outside and potassium to the inside. And you notice for every three sodiums pumped out, we're going to have two potassiums inside. And that alone helps to explain why we're going to have differences in charge. Now, both of these ions are positively charged. And there's going to be more than three and two. There's going to be lots. Then we have our potassiums, and because we have sodiums on the outside and potassiums on the inside, they're going to want to move to the other side of the membrane through simple diffusion. But they can't because the membrane is impermeable to charged particles. Now, in addition to our potassiums on the inside, which are really lesser in number than the sodiums on the outside, because that's the way the sodium potassium pump determines it. Also, there may be a couple of potassiums on the outside. There may be a sodium or two on the inside. But we have the greater concentration of sodium on the outside, greater concentration of potassium on the inside. In addition, we have anions on the inside. These are proteins or maybe some other bicarbonate or something like that are known as A negatives. A negative. A negative. A negative. So that's anion negative. All anions are negatively charged. Reason I'm pointing that out is you can see that we have more sodium ions on the outside and less more potassiums on the inside, just less in number as the outside. And with these negative ions, you can see that we're kind of getting more positively charged on the outside of the cell, less positively charged on the inside. So that actually creates polarity or a voltage in the membrane. It is positive on the outside, negative on the inside. Now, as I said before, the plasma membrane is impermeable to charged particles. So, in order for sodium to get in the cell, in order for potassium to move out, we're going to need channels. And there's three basic channels we need to know about. The first one are called leakage channels. So I'll write that down here, leakage channels. And what they do is they're in the membrane all over the place, and they're always open. So here's a leakage channel. There's a leakage channel, and so on. So here's our leakage channel. And what these do is they allow sodium to move in. They allow potassium to move out. But again, the sodium potassium pump pumps them back in or out as soon as that takes place. So the resting membrane potential is kept in check. Now, another thing to know is that, let's say this is the potassium leakage channel. The potassium leakage channel lets more potassium out than the sodium channel allows sodium in. That further determines or makes the fact that we have a positive charge outside of the cell and a negative charge on the inside. And that voltage, there is actually a number. We'd have a 9-volt battery. In this case, we have a negative 70 millivolt membrane. So we see over here, we have negative 70 millivolts. That's going to be important in just a minute. But for right now, we know we have a charge, a high charge on the outside, low charge on the inside. So I said before, those ions want to move by diffusion from high to low. So we have chemical gradients for both sodium and potassium. Also, because we have these opposite charges, positive, negative, those charges are attracted to one another. So we have an electrical gradient. When you put them all together, we get an electrochemical gradient. And again, the leakage channels allow for a few to move back and forth all the time, but the sodium potassium pump equalizes that. Now, as I said before, here we have our cell body and the dendrites. The cell body and dendrites receive stimuli from other neurons. And this is done through neurotransmitters. Neurotransmitters are released by, let's say, here's another neuron releasing neurotransmitters. Well, what are those neurotransmitters supposed to do? That brings us to our second channel, which is a chemically gated channel. Sometimes it's called a ligand-gated channel, because that chemical we're talking about is neurotransmitters. So ligands, there's many different kinds of neurotransmitters. We just group them together as one group of ligands. Now, how does this work? Well, we have our leakage channels over here. By the way, our sodiums are over here, just as much as over there. Our potassiums are over here. Now, what a leakage or chemically gated channel does is they're shaped in a way that there is a binding site for those neurotransmitters. So here's our chemically gated channel. It is closed. But if that neurotransmitter attaches to this binding site, that's going to open up the chemically gated channel. And in this case, it's usually sodium that rushes in. So when that happens, sodium rushes in, and all of a sudden we have these potassiums and sodiums all joined together here at that local region. Now, because all these sodiums and potassiums are now grouped together and they're all positively charged, they're going to want to get away from each other. They repel one another. So because we have all these sodiums rushing in, we're actually going to change the voltage of the membrane temporarily. Let's say it goes down to negative 65. Well, that's going to quickly change. Number one, that chemically gated channel is going to close. It opens and closes very quickly as long as those neurotransmitters are not there. So if we have a few neurotransmitters there, they open and close quickly because those neurotransmitters only stick around for a very short period of time. So we let the sodiums rush in, then that neurotransmitter disappears and the chemically gated channel closes again. When that happens, we have that change in voltage. We have those sodiums and potassiums all together, but because they're pushing away from one another, we get what's known as or they're spreading away from one another. We get what's known as electronic spread. And what this does is push the ions apart, the sodiums get pumped back out, and that negative 65 dissipates back to that negative 70 resting membrane potential. Now, if there's a whole lot of neurotransmitters released, or many neurons are releasing a bunch of neurotransmitters, these chemically gated channels are going to be open for longer periods of time. And what will happen is we get more and more and more and more and more and more and more sodium in there. And that's going to cause a greater change of voltage. If it reaches negative 55 millivolts, that's said to be a threshold voltage. What do I mean by that? Well, the third type of channel we have are called voltage-gated channels. They begin in the axon hillock, which is right around there where this leakage channel is, and they will be found along the entire stretch of the axon, voltage-gated channels. And the way these work is a voltage-gated channel will only open if there's enough of a change in voltage from these, what are known as graded potentials. Graded potentials are the chemically gated channels. When a voltage-gated channel opens, that's an all or none phenomena. Once these voltage-gated channels open, it's all over. We're going into an action potential. So here's I'll give them a little jagged end to make them look like a lightning bolt. But when these voltage-gated channels open, by the way, this has a little thing on the side here. When this opens, sodium is going to rush in like crazy. So much sodium is going to rush in that the membrane is literally going to go from negative 70 millivolts all the way up to positive 30 millivolts. Now we have these, that's a sodium channel, sodium voltage gated channel. When it opens, it's going to allow all those sodiums in, and we get a change of 100 millivolts. That's going to close once that 30 millivolts is reached, and the next voltage gated channel is going to be a potassium gated channel. So we'll do the lightning bolt backwards. When these open, by the way, all these sodiums are gone because they went inside the cell. When the potassiums open, also we have these potassiums on the outside of the cell. This is actually going to change the polarity of the cell from positive to negative to positive. So we'll actually get negative on the outside of the cell and positive on the inside of the cell. And that's going to go all the way to negative 90 millivolts, which you can hopefully see over here. Negative 90 millivolts. By the way, this is a voltmeter. Say we had a little box and we were measuring the electricity in this membrane. We could literally measure it with a voltmeter. So that negative 70 millivolts, that's our resting membrane potential. And that's the way it'll stay as long as the leakage, the chemically and voltage gated channels remain closed. But here we've got those voltage gated channels opening and all hell breaks loose. We go from a negative 70, let me start over. A graded potential, which we saw up here, is going to be just a little change in the voltage of the membrane. It's going to have electronic spread, it's going to dissipate, and the membrane will go back to negative 70. So that's a graded potential. It happens, but it doesn't cause anything to happen. It's as if nothing ever happened as far as you're concerned. But that's a graded potential. But if we have a strong enough change in the voltage where we reach that threshold, well, then the voltage gated channels open and boom, we go all the way to positive 30 as the sodium channels remain open. When we reach that negative or positive 30, the voltage gated channels close. This thing closes. And the potassium gated channels open so that the potassium rushes out. When that happens, the voltage is going to change back to negative 70 and beyond. So we go from negative 70 all the way up to positive 30 because we're changing the polarity of the membrane. It's called depolarization. I'll just put depolar. So that's depolarization. When this potassium voltage gated channels open, then we're going to get repolarization. We're going to go back to that negative 70. So that's called repolarization. And because it goes all the way down to negative 90, we get what's known as hyperactive, hyperpolar. Hyperpolarization. And then the sodium potassium pump, which is always working, will return, oops, I did that wrong. This will go all the way down to hyperpolarization, and then it will come back up to resting membrane potential thanks to the sodium potassium pump. That is an action potential. Now that only happens on one little area of the membrane, but the neighboring voltage gated channel will feel that change in voltage. It will open, sodium will rush in, then the potassium channels open, potassium rushes out, and we'd have another action potential. And then another. And then another. And that's basically the way a nerve impulse works. We have a propagation of one action potential after another, after another, after another, until you reach the end of the axon. Now that's a mess, isn't it? So I'll erase it all. And we'll start with the voltmeter again. So here's our voltmeter. There's our resting membrane potential. Again, when we have an action potential, there's our threshold. Negative 55 is our threshold. That threshold has to be met. That's a change in voltage, has to be met in order to have an action potential. So let's say our graded potentials are taking place, keep going. All of a sudden, boom, we've reached that threshold. Now the voltage gated channels have opened, and we're going to have our depolarization. Depolarization. polarization. Then when we hit positive 30, let's say it's right here, positive 30, the sodium voltage gates close and the potassium voltage gated channels open. Then we have repolarization. And that repolarization goes all the way down to negative 90. That's called hyperpolarization. So repolar, hyper, polar. And then the sodium potassium pump just puts the membrane back to the resting membrane potential. Now, when this is taking place, there's this action potential by itself inhibits or completely stops another action potential from taking place until this one is done. So let me explain how that works. These are known as refractory periods, and there's two refractory periods. The first one takes place during depolarization. Because those sodium voltage gated channels are open, there's no chance for another action potential from taking place because the sodium channels are already open. So that's called an absolute refractory period. This is the first one. Absolute refractory, period. Now, once the sodium channels close and the potassium channels open, well, with the sodium channels closed, I guess you could have another sodium ion or the sodium voltage channel is ready to open again. It's closed, right? Well, because during this refractory period, which is much longer, because the after repolarization, the voltage goes all the way down to negative 90, going from negative 90 up to the threshold is much more difficult than when you have your average action potential. So this is called the relative refractory period. Relative refractory period. This is called the relative refractory period because if there's a strong enough stimulus from the dendrites or the cell body or both, you got a whole bunch of neurotransmitters being released. You're sitting on attack. A whole bunch of neurotransmitters being released. You could have a stimulus that is so strong that it could actually cause the cell membrane to go from negative 90 all the way up to negative 55, so that the another action potential can be initiated even before this one is done. So that would be known as the relative refractory period. Now, I could talk about how to speed up a nerve impulse, but I'll leave that for another day. That, my friends, is an action potential. Thank you. Have a great day.